Hello, we're going to talk about forces some more, specifically Newton's second law this time. So as a reminder, Newton's first law says an object with no forces acting on it, if it is at rest, it will remain at rest, and if it is in motion, it will remain in motion. And really what this is saying is that forces are necessary to change motion. That does not mean an object can only move when a force acts on it. Instead, it means that a force is needed to get an object to start moving, but it will keep moving until another force acts on it. So again, force is needed to change motion. You can also think of this as a force is needed to start and stop motion. So that was Newton's first law. Newton's second law says an object that is subject to multiple forces will undergo an acceleration. So if you were in class on Tuesday, I talked about this idea a little bit. The idea that if there is a net force on an object, then it must be accelerating. So let's think on this a little bit more. So we have a situation where a person is applying the same force to two different objects. The objects, sorry, it's blurry, but the objects are the basketball or a basketball in a car. So we're only looking at this force applied by the person, but we're saying, okay, that is our net force in this situation. If there's net force, there must also be a net acceleration. But we can look and see this diagram indicates that the acceleration of the basketball is way different than the acceleration of the car. And this is also something you can pull from your own experience. Like, you know that if you push on a basketball the same way you're pushing on a car, the basketball is going to move way more than the car. And so that movement, that motion that is happening is the acceleration of the object. So that's one big difference, is that even though the same force is being applied, the accelerations are different. But there's another big difference between these objects, and that is the mass. And remember, or it's helpful to think of mass as how hard it is to get an object moving. So like I've already said in a different way, it is way easier for the person to move the basketball than it is for them to move the car, because the basketball is much less massive than the car. So in general, it's easier to get a basketball moving than it is to get a car moving. I mean, if you're just like pushing on it. Oh, and I have that down here, that a mass is how hard it is to get an object to move. So the forces are the same, but the masses and accelerations are not. And we can use this to see that acceleration of an object experiencing a net force depends on the force itself and the mass of the object. So just because the forces are the same doesn't mean that the accelerations will be the same if the masses are different. And so this gives us an additional kind of thing to think about when we're talking about Newton's second law. And that is this equation where we're saying the net force on our object is equal to its mass times the acceleration of the object. And net force is just the vector sum of all the forces acting on the object. So if we have, an example here, 3 forces acting on the object, we would sum up those vectors, and that gives us the net force. And something important with forces is the units. We have a unique set of units now, or unique unit itself. So the units of force is newtons. It's given by a capital N, and it's kilograms times meters divided by seconds squared. So kilograms, that's mass, and meters per second squared is acceleration. So if you ever forget what newtons stand for, just go back to the Newton's second law equation, which is force equals mass times acceleration. And that will help remind you what the units are or what a Newton is. Oh, I'm sorry, this is blurry too. This is just to kind of help you get a picture of Newtons. Here are some approximate magnitudes of things in Newtons. So the US nickel is about 0.05 Newtons. A quarter of a cup of sugar is about half a Newton. 1 pound object is 5 Newtons. A typical house cat is 50 Newtons. And my cats are pretty big, so they're definitely more than that. The weight of a 110-pound person is 500 Newtons. And so there's the other examples that you can read, but I also want to say, and I think that the quarter cup of sugar kind of is as close to this as it gets, but I believe that a Newton is also the equivalent to the weight of kind of an average apple. There's a lot of range there because apples are very different sizes. But if you can think about picking up an apple, for the most part, that's about a Newton. But if it helps instead to think about the weight of a quarter cup of sugar for half a Newton, or the weight, it's a little funny that they did a quarter cup of sugar instead of half a cup of sugar, which would be 1 Newton. Interesting. I think they wanted to go by fives, actually. Never mind. So here is an example where we have two forces acting on an object with these kind of more faded reds. Force 1 pointing down, force 2 pointing to the right. And then using vector addition, we can find the net force pointing in this direction. But something to keep in mind is that the acceleration is also in the same direction as the net force. So we have our net force, that means our acceleration also kind of points down and to the right. So I have a question for you to kind of pause and think about, but then I'll also go over the answer. So what is the direction of the net force on this object? Also, I just realized something funny about this, and I will tell you what it is in a moment. So force 1 is pointing to the right, force 2 is pointing down. Which one of these shows the net force on this object? So pause here if you want to figure this out yourself. Otherwise, I just moved force 2 over because this is how we do vector addition. We do the first vector, and then we draw the second vector starting from the tip of the first vector. And then we put our total vector, our net force in this case, from the tail of the first vector to the tip of the second one. Also, the thing I realized is on the previous slide, let me go back. The forces are the same. So I changed the labels, but I only just realized this. I gave you the answer, net force, because these are the two forces on there. So anyway, that was my bad. But the answer to this one is C. And then I asked you, what is the direction of the acceleration of this object? So pause, think about the answer to this yourself. But also, this is an answer I gave you too. Because on that slide, I also showed you that the acceleration is in the same direction as the net force. And if the net force is represented by this vector C, the acceleration also is. Okay, now I want to spend a little bit of time with free body diagrams and kind of expanding our understanding of them. So we want to know which of these free body diagrams shows a ball thrown straight up. And so to answer this, you want to think about which forces are acting. And you want to remember that Newton's first law says just because something is moving up it doesn't mean that it has to have a force also moving in that direction. Okay, so think on this. But the forces acting, we know for sure the weight forces because this is near the surface of the earth and weight is always acting and that points down. Can we think of any forces that would be pointing up in this case? You might be able to think of some other forces that could act, like drag, for example. Totally relevant. But if our object is moving up, drag would need to point down, and there's no free body diagrams with two down vectors. So I can't think of an upward force in this situation. So I'm gonna say the answer is C, this single vector which is represented or which represents the weight force. Now, you're gonna hear me refer to this idea, especially, I mean, like now for the next couple of weeks while we're working on forces, and I call it force equations. And the idea is that you can generate equations like that show the relationship between forces acting on an object just from your free body diagram. So before, if you think back to Monday, we did the free body diagram of a book on a table. But in general, the policy is that free body diagrams go on a coordinate plane. So we have the y in vertical and x in horizontal. So I'm just going to move those vectors over there. So now they're in the right place. The next thing to do is generate those equations. So we know we have that place to start from, right? We have the net force is equal to the mass times the acceleration. So we have that part, but then what is the net force? The net force is just the sum of the forces acting. And so we have the normal force in the positive y direction and the weight force in the negative y direction. So summing those together really means subtracting the weight force from the normal force. So that puts us with this equation. The net force in y equals the mass times the acceleration, which is equal to the normal force minus the weight. But one thing we find in this situation, you can see this in a couple of ways. First of all, just in the vectors themselves, these vectors are the same size. They point in different directions, but they're the same size, which means our net force here is 0. Another way that you can come to that same conclusion is this object accelerating in any direction that you can think of? And in this case, because our forces are just vertical, we can just focus on the vertical. Is this book accelerating through the table or up into the air? No. So the net force must be 0. I'm going to take these equations to the next slide. So we have that the net force in y is mass times acceleration, which is equal to the normal force minus the weight force. Then we said, okay, actually the net force is 0. So let's bring that into the relationship between normal force and work. So we see that the normal force minus the work is equal to 0. And if we add the work, I'm so sorry, I said work, weight. If we add the weight to both sides, we find that the normal force equals the weight. And there's one more thing that we know here, and that is the equation for weight. Weight is given by mass times the local free fall acceleration or acceleration due to gravity. So just mg. And remember, this is the same g that we use for acceleration in the y direction. And one thing to note is when we plug that g into equations for acceleration in y, when we're solving like projectile motion problems, we make it negative. But we already incorporated the negative in the beginning. We said the weight force points down, so it's negative. So we don't have to worry about the sign of the gravitational acceleration here. So now I want to do a few examples of this where we figure out the forces, draw the free body diagram, and get the equations. What? Okay. So now the first example is a ball rolling to the right and slowing down. So first we'll just draw that. We have a ball on the ground. It's rolling to the right, and that's our velocity. And then it's slowing down. So we'll start with just what forces are acting. So weight and normal force. Weight because we're on the earth, normal force because it's on the ground, it's touching a surface, so there's a normal force. And then we'll pause. There is potentially another force, but I want to draw these two on our free body diagram first. So weight force, that points down. Oops. There we go. Wait. Normal force points up, or it points perpendicular to the surface, and the surface is the ground, so it points up. So we have those forces. But we have a situation where the ball is moving to the right and slowing down, which means there's acceleration. And that would be in the plane that motion is happening in. So, and what I mean by that is it's not accelerating up or down because it's not moving up or down, but it is moving right or left. So acceleration must also be right or left. So then, the next thing to think about is, okay, my velocity is to the right and we're slowing down, which means my acceleration is in the opposite direction. So that means my acceleration should go to the left. So that tells me I need a force that points to the left. Okay? So that my acceleration and my net, sorry, I might accidentally write sum of forces, but I'm trying to keep it as net force for you. But yeah, so I have to have a force there that is causing this acceleration. And the force, the kind of simplest answer for what that force would be is the thing that slows every rolling object down. It's friction. So we can say friction is our third force. And so this is kinetic friction because it's moving. If it wasn't moving, it would be static friction. So that's the kind of curly F and the subscript K for kinetic. Awesome. Okay, so we have our forces and we also know what direction our net force is in and what direction our acceleration is in. So we can see just looking at our free body diagram that the net force in Y is 0 because we have the normal force and the weight force, and those are the same size but point in opposite directions, so they cancel each other out. And also another way we can think about that is just the ball is not accelerating up into the air or down through the floor. So the net force in Y must be 0. So we will write that as F net Y equals 0, and that equals the normal force, which is pointing up, so that we'll write that first. And then the weight force is pointing down, so we say subtract the weight force. Okay? Now we want to do the same thing for the x direction. So net force in x, this time we know there is acceleration in the x direction. We drew it. That's the x direction. It's negative x direction. So that tells us that this is not equal to 0. It's equal to mass times acceleration. But I'm going to do something important here is, well, first I'll write mass. but this acceleration is in the negative x direction. It's negative. So negative acceleration. So this is a place where you have to remember to bring in the sign from your diagram. And that's true for the forces and the acceleration. The acceleration was down, for example, it would be negative also. That would be the acceleration in y. But if the acceleration in y is up, it would be positive, and if the acceleration in x was to the right, it would also be positive. Okay, so we have mass times negative acceleration, because again, it's to the left, which is negative. And then the only force we have in x is that kinetic friction force. It also points to the left, so it's also negative. Okay, so that is our force equations for this example. We would need more information to do anything else. Plus, we haven't even talked about how to find friction yet. So this is a good ending point for this example. Next example is the one from the Monday post lecture again. We have a child pulling a sled by a string at a constant speed with friction between the sled and the snow. So, sled, child. They're moving this direction. And the ground. And there's friction between those. So, well, we can start right there, I guess. Friction, because it says, and let's see, it's the kid is pulling the sled by a rope or a string. So that tells us there's tension. And then the other two that are usually there, or they're going to be there if something is sitting on a surface, and that's going to be normal force and the weight force. Okay. I guess we could think about other forces that might act, and there could be drag because there's velocity, but this kid, it's a child. They're not pulling the sled that fast, and the sled doesn't have a ton of surface area. So I think we are safe to assume that drag or air resistance isn't affecting this. And this isn't a rocket sled, so there's no thrust. There's no spring, so there's no spring force. So yeah, I think we're safe with those four forces. Then we draw our free body diagram. So I'm going to draw normal force and weight first, because I know there's no acceleration in the vertical direction. So weight points down, normal force points up, and they're pretty much the same size. They're supposed to be the same size, but actually, I'm sorry, I just realized I put this, oh, don't want to erase stuff. I put the sled at an angle, theta. So actually, the normal force and the weight force don't have to balance each other perfectly, because we have another force in the y direction, which is the y component of the tension force. So we have the weight force. Then I'm going to draw the tension force. So something kind of like that, and that's our angle tension. And then we also have, let's say that's the normal force. It's not perfect. Well, maybe I'll just make the weight force bigger, actually. Yeah, we will do that. All right. Okay, weight force bigger. I think that's right. Weight force. And then the last thing we have is the friction force. And so the friction force is going to point opposite the direction of motion. We've drawn the child moving to the right, so friction is going to point to the left. And then it says at a constant speed. That means that the net force is 0. So we need to make sure the forces cancel out in the x direction too. So before I draw the friction force, I want to point out that here is our X component of the tension force. Okay, so our friction force needs to be that same magnitude in the opposite direction. So pretty much that, yeah. Friction, and it's kinetic because we're moving. And then I'm also going to add on here the Y component of the tension force, Ty. And now we have our free body diagram. We know the net force is 0 in both directions. So we can start with Y, F net Y equals 0. And then let's look at what forces we have in Y and whether they're positive or negative. So we have the normal force, that's positive. We can put that there. And then we have the Y component of the tension, also positive. So we'll put that as positive. And then finally, we have the weight, which is negative. So we subtract that. Okay. And then in the X direction, so F net X is also 0. And the positive force we have, or the one that's pointing in the positive X, is the X component of the tension. That one's first, TX, and it's positive. And then the friction is pointing in the negative X, so we subtract that. Okay, so those are the force equations for this example. We could do a little bit more, but we'll, by breaking up or writing the equation for what tension in Y and tension in X are, but we'll actually just do that in the next example. So I'm going to skip it for this one. Okay, last example, and this time we have numbers, so we can actually calculate something. So we have a tightrope walker, and we're asked to find the tension in the wire supporting them, and we're told their mass, which is 70 kilograms. So this one already tells us what forces are acting, because it already kind of draws us a free body diagram here. So we have the weight force going down, and then we have these two tension forces going up at a certain angle. So let's draw our free body diagram. I know they gave us one, but I still want to put it on an XY coordinate axis. So we have the weight force pointing down. And then, so they're labeling these tensions T sub R for tension to the right and then tension to the left. So let's do that too. So let's see. Tension. Oh, that's too big. Try like that. Yeah. So this is tension R. And this one, trying to make it about the same. Tension L. I don't want to put that there because the angle they gave us is this one here, which is a little bit weird. Theta, so this is TL, and this is theta L. And this is theta R. Yeah, okay. So that's our free body diagram. The thing to keep in mind, though, is that we have X and Y components of these tensions. They're at an angle. So we have X and Y components. So the X component is going to be here. And that is also adjacent to this angle. So they gave us that angle up there, but just with how angles work, it's also the same one. So don't stress about that part right now. So this is also theta L. So okay, we have the tension on the right in X, and then we have the tension on the right in Y. Yes. And then we have the one on the left. So TLX and TLY. TLY. So one thing we can assume with this, in part because they don't say anything about acceleration. They don't say like the person is, accelerating down or something. So we're pretty safe to assume that the net force is 0. But my drawing doesn't have that. My weight force needs to be bigger because there's these two forces, the two tension forces in Y add up to be bigger than my weight force. So that would imply that they're accelerating up. And that's not what's happening. So let's redraw that. And keep in mind, you're always free to redraw if you realize, oops, one of my forces was wrong. Like wrong size or something like that. Okay. Then I'm going to kind of zoom in on just one of the tension forces. So here's our theta. I guess this is going to be tension in R because that's the direction I drew. And then we have our Y component, TRY, and TRX. So, and this is just like when we do other stuff with X and Y components, we have an angle, and so based on where the X and Y components are situated with respect to that angle, that's how we define it. So the Y direction is going to be TR sine theta because Y is opposite the angle, and TRX is TR cosine theta R, I guess. So this is the same thing for the left tension too. So I'm not going to draw it again, but it will also be TLY is TL sine theta L, and TLX is TL cosine theta L. Okay. Now that we have all of that, we can create our equations. First thing though is net force equals 0. So that tells us that we're 0 in X and Y. So start with Y, I guess, or X. Yeah, let's start with X. F net X equals 0. And we just have that. The only things in X are the X components of the tension. The right one is positive, so that goes first. And then the left one points to negative X, so it's negative, and we'll put that second. Okay, we'll leave that for now. And then we'll do Y, it also equals 0. And then let's look at our free body diagram, because again, these equations come right from your diagram of the situation. So we see that in the positive Y direction, we have these two Y components of the forces, of the tension forces. So TRY plus TLY. And those are positive because, again, they point in the positive Y direction. And then we subtract the weight from them. Okay, cool. So this time, though, we're not just stopping there. We're going to solve for the tension. So we have these two equations. Let's start with kind of solving this X one and seeing what information we can get. We have 0 equals, and then I'm going to plug in our equations for TRX and TLX. So we end up with TR cosine theta R, and then minus TL cosine theta L. And then we can add the left one to the other side. And so we end up with TL, the whole thing, cosine theta L equals TR cosine theta R. So there's something else we can get from our diagram, and that's that the angle, well, it is in our diagram, but I'm sorry, I mean the diagram they gave us. So the angle here is 5 degrees for both of them. So theta R equals theta L, which means we can actually cancel out these cosines because they're the same and both terms are multiplied by them. So goodbye cosine. And what we find is that the tension to the left is equal to the tension to the right. So that doesn't tell us what the tension is, but it does simplify things for the next equation. So let's do that one. See, 0 equals, and here we will plug in the equations for the tension. So TR sine theta R plus TL sine theta L minus weight. Okay, and one thing we can do, because again, we found just now that tension in L equals tension in R, and we also just said that the angles are equal. So we can actually just combine these, and I think I'll just call it tension sine theta, but there's two of them, so we have to put a 2 in front. Okay, so 0 equals 2 times the tension times sine of theta minus the weight. So again, we're solving for tension, so let's add the weight to both sides. So yeah, so we get weight equals 2 times the tension times sine theta. Then again, because we're solving for tension, let's divide 2 sine theta on both sides to get tension by itself. So weight divided by 2 sine theta equals the tension. And then the equation for weight, remember, is the mass times acceleration due to gravity. And we don't have to make that negative because we brought the negative sign in way at the beginning when we were making these equations. So mg over 2 sine theta. And then the mass they gave us was 70 kilograms. G is 9.8 meters per second squared, divided by 2 times sine of 5 degrees. And this gives us a tension of about 3,900 newtons. I'm rounding because I don't have the exact number up in front of me and I don't want to get the wrong one. But this, for such a big number, it's okay to be less precise. So that is our tension. And we got all of that. We didn't use some like special set of equations for solving these force problems. The only equation we really used is the net force equals mass times acceleration. And then we got all of this from our free body diagram that we drew, and it gave us all the information we needed to find the tension. Okay, so we're going to be practicing lots more of this, but that's all I have for you today. So have a great day.